Why does humanity feel more ignorant the more we learn about the universe? Setting philosophy aside, even with what we can see, measure, and study, why do our theories and models seem so powerless? Over the next 50 minutes, we'll explore cutting-edge physics and hypotheses, discussing controversial cosmic mysteries. Mystery number 1, the cold spot. Imagine you're looking at a map of the universe's oldest light, the cosmic microwave background. It looks mostly like TV static. Tiny temperature variations across the sky, barely noticeable. This is exactly what scientists expected. Small, random fluctuations. Nothing too extreme. But there's one spot that's unusually cold. Not just slightly below average temperature, but clearly out of place, like a splash of ink on a white wall. Strikingly obvious. After all these years, no one can explain why it exists. This region, called the cold spot, was first discovered by NASA's WMAP satellite in the early 21st century. Later, Europe's Planck satellite confirmed its existence in 2013. So this isn't a sensor malfunction or data processing error. It's genuinely real. Located in the direction of Eridanus, spanning a massive elliptical region of about 1.8 billion light-years, it's an anomaly in cosmology. Colder than everything around it. And this cold is extraordinary. It doesn't fit the universal laws of cosmic evolution. Theoretically, the early universe should have been nearly perfectly uniform. The tiny temperature variations in the CMB were the seeds that later formed galaxies and galaxy clusters. But even these variations follow a statistical pattern. The cold spot clearly defies logic. So people began wondering if something was blocking or distorting the light. This led to the supervoid hypothesis. Perhaps between us and the cold spot, there's a massive empty region with extremely low matter density, causing light to lose energy on its way to Earth. This would theoretically make that region appear colder than it actually is. And there is indeed a void in that direction. But it's not big enough or deep enough. If the cold spot is a giant crater, this void is at best a small puddle. No, we're near enough to fill it. So, this explanation doesn't truly solve the problem. Another possibility is coincidence. A 1 in a million coincidence. Something that just happened in a random universe. But when you are dealing with data spanning billions of light years, this explanation is hard to swallow. So more extreme ideas emerged. What if it's a sign of something beyond our universe? Perhaps it's a scar left behind from our universe colliding with another universe. This isn't science fiction nonsense, but a possibility proposed by physicists. A serious, though still speculative, explanation. This idea suggests that if our universe bubble, while expanding, once collided with another universe bubble, it could leave such a mark. However, this theory is in mainstream. It's a huge leap. Using another universe as an explanation sounds cool, but it's like solving one mystery by creating an even bigger mystery. So, the cold spot remains an unsolved case. Mystery number 2, dark flow. You might think that by now, we should know exactly how the universe moves. Everything expands outward. Galaxies move away from each other, and the farther away objects are, the faster they recede from us. This concept of cosmic expansion was proposed by Edwin Hubble over a century ago and has long been confirmed. But then, a motion that doesn't follow expansion laws emerged. A large-scale drift. As if the entire universe is being pulled by some invisible force. This isn't just a few galaxies, but thousands of galaxy clusters, all moving in the same direction, as if drawn by a massive invisible hand. This motion was discovered by astronomers in the late 20th century. They studied the cosmic microwave background through kinematic, Sun-Yov, Zeldovich effect, and noticed these galaxy clusters weren't stationary relative to background radiation, but collectively drifting, all toward the same region of sky, near Centaurus and Vela constellations. This motion is called dark flow. Galaxies are always moving. That's normal. Gravity pulls celestial objects. Local galaxy clusters interact. Space itself is expanding. But this flow is different. It's massive in scale, uniform in direction, and persistent. It's not caused by nearby structures, like the Great Attractor or Shapley supercluster. These factors have been considered and ruled out. This is something bigger, more distant, and stranger. One of the biggest questions is what's causing this drift? Because if space expands uniformly in all directions, there shouldn't be a single direction where all objects collectively converge. But the data confirms this situation. So scientists began checking for errors again. But year after year, subsequent studies kept finding signs of the same drift. Measurements were questioned, corrected, and re-verified. But the concept of dark flow never fully disappeared. The current mainstream view tends to consider it unconfirmed. But the initial results were alarming enough. Because if these results are correct, it means something is happening beyond our observable universe. While our observable universe has a radius of 46 billion light-years, just because we can't see doesn't mean there's nothing beyond that boundary. The existence of dark flow suggests that beyond that boundary, there might exist something that can pull our entire galaxy cluster. Something unimaginably massive. And we don't know what it is. Nor can we observe it. This leads to some bold ideas. One is the multiverse. Other universes floating beyond our universe, each as independent bubbles. Perhaps one of these nearby, larger universe bubbles, has a gravitational effect on us. Not in a science fiction sense, but on a physical level. Another idea is, the early universe may have had structures far more massive than anything in our models. Massive enough to leave gravitational imprints. And we're only now beginning to detect these imprints. These might not be galaxies, but superstructures capable of reshaping space-time itself. Of course, there's a simpler possibility. Perhaps we're just misreading the data. What we call dark flow might just be an illusion caused by some local distortion we don't fully understand yet. This explanation is undoubtedly simpler. Some recent studies also lean in this direction. But the problem is we still don't know the truth. Dark flow is one of those phenomena hovering on the edge of data and speculation among cosmic mysteries. Some researchers have stopped focusing on it, considering the evidence insufficient. Others continue deep investigations and simulations, improving measurements, trying to determine whether this is a minor data glitch or a clue pointing to a grander picture. Mystery number 3. Tabby's star. We've studied thousands of stars. So, when a star begins dimming in a way that doesn't follow any known rules, people take notice. And when this dimming is irregular and unpredictable, people start getting confused. This star, about 1,470 light-years from Earth. At first glance, it's nothing special. Just an ordinary F-type main sequence star. Slightly hotter than our Sun, and a bit larger. But what makes it unique isn't what it does, but what it doesn't do? When astronomers looked at Kepler telescope data, Tabby's star stood out. It doesn't just dim, but dramatically drops in brightness. Sometimes by 5%, sometimes 15%, and once by over 22%. This scale is enormous. Consider this: when a Jupiter-sized planet passes in front of a star, it typically dims the brightness by only about 1%. So, to block 22% of a star's light, that object must be massive. But even so, this dimming should be regular, cycling repeatedly because planets orbit in fixed, periodic cycles. But Tabby's star dimming events have no fixed timing, no symmetry, just unpredictable brightness drops, followed by long periods of calm. Some suggested a comet cloud, or a dust disk, or some debris field around the star. But these ideas don't hold up. For example, the comet theory requires an extremely massive comet swarm, in exaggerated numbers, moving in just the right way to create that pattern. Even then, it can't explain this star's overall dimming. Year after year. Next, Comey's, the part that captured widespread public attention. The alien theory. Some scientists cautiously proposed an idea. Perhaps it's a Dyson sphere built by an advanced civilization. Though this wasn't taken seriously, it was more of a last resort explanation. But once this idea was proposed, it captured imaginations. Think about it: a normal star showing completely abnormal behavior. So abnormal, we had to consider artificial causes. This is extremely rare in astronomy. Of course, more grounded theories followed. Some scientists proposed it might be caused by irregular interstellar dust clouds. These dust particles filter certain wavelengths more than others, causing strange dimming patterns. But so far, even after years of monitoring and analysis, we still don't know what's happening. All mainstream theories fail to explain all the observations. Its strangeness persists. Every time new data arrives, it seems to raise more questions than answers. Although the alien hypothesis has been largely shelved, what exactly are we looking at? An exotic star type we've never seen? Or a cloud of matter that doesn't quite match our physics? Or something else entirely? In any case, Tabby's star reminds us that even in fields we think we understand, there are still things we cannot explain. Mystery number 4, the cosmic silence. We've pointed radio telescopes at the sky for decades. We've been listening, searching for patterns that might suggest intelligent life beyond Earth, pulses or any signals. We've also sent messages outward. Radio broadcasts, binary code, even a spacecraft carrying a golden record, engraved with instructions and music, just in case someone or something finds it. Yet, nothing. This silence is strange. Because the universe is old. The number of stars is almost incalculable. Many of these stars have planets. Some of these planets are inhabitable zones, where liquid water can exist. Given enough time, life should emerge. And intelligent life shouldn't be that rare. But what's strange isn't just the silence, but the persistence of this silence. The only signal that ever caught attention wasn't because it was complex or detailed, but because it was so weird. The WOW signal detected by astronomer Jerry Emin in 1977. The WOW signal. It lasted 72 seconds. Extremely intense. Coming from a region of sky that shouldn't emit any signals, the astronomer who saw the printed signal peak circled it and wrote WOW next to it. That's how it got its name. To this day, no one knows what caused it. It never appeared again. No single explanation can fully account for its characteristics. It's like hearing a voice in a crowd that vanishes before you can turn to look. Then there are fast radio bursts, FRBS. Brief, sharp bursts of radio waves, lasting only milliseconds. The first was discovered in 2007, almost by accident. Since then, we've found dozens. Most don't repeat, a few do. Some come from distant galaxies. They release enormous energy, far exceeding what stars like our Sun produce in the same time frame. We still don't know what causes them to appear. The best guesses point to neutron stars or magnetars. These exotic high-energy objects that can produce intense radio pulses. Others think it's merging black holes or extreme magnetic fields that distort space in ways we don't understand. These are all possible, but currently no single theory can explain all types of fast radio bursts. There was one case, a signal repeating in a 16-day periodic pattern, that made headlines. Because randomness is one thing, but structure and repetition spark curiosity. Even so, that one was also attributed to natural causes, possibly a binary system, or an object orbiting near a strong emission source. The problem is we don't have clear answers. We have data, signal peaks, flashes and anomalies, but nothing clearly pointing to intelligent life. This raises another possibility. Maybe we're just listening wrong. Maybe we're scanning the wrong frequencies. Maybe civilizations don't use radio. Or maybe they don't want to talk. Scientists have started seriously considering a possibility, similar to the dark forest theory from 3-Body, that advanced life might deliberately stay silent, out of caution, principle, or fear. It's also possible we emerged early. Perhaps intelligent life is still rare, and we're among the first civilizations to reach this stage that would make us pioneers. Or these civilizations have lifespans, and the time windows for two advanced species to communicate simply don't align. Or maybe life is out there, but it's completely different from what we imagine. No cities, no technology, no radio. Maybe intelligence evolved in ways we can't detect. Perhaps under ice sheets, in atmospheres, on gas giant planets. Maybe life exists, but it doesn't care about communication. In any case, this silence remains a mystery. We know the conditions for life exist. We know life's building blocks. Carbon, water, energy are everywhere. But when we look up, we see no signs of anyone else using them. Perhaps that's what makes this mystery so peculiar. It's not about what we've heard, but what we haven't heard. Not the absence of noise, but the absence of evidence in a universe that should be full of it. The more we listen, the more we realize that this silence itself might be telling us something. Mystery number 5. The axis of evil. In theory, our universe should be perfectly fair and balanced. No matter which direction you look, as long as you look far enough, it should all be uniform, like sprinkling pepper, roughly the same everywhere. This is a fundamental assumption of modern physics, called isotropy. But the problem is, the universe seems not to follow this rule. Scientists studied the afterglow of the Big Bang, the cosmic microwave background radiation. They expected to see a bunch of random, chaotic temperature spots. Most of it was indeed like that. But within this randomness, they found a pattern that shouldn't exist. Large patches of temperature regions, eerily pointing in the same direction. They lined up neatly along a single axis, stretching across the entire sky. This discovery was so shocking that scientists half-jokingly gave it a name: the axis of evil. You might think, what's the big deal if the universe has a preferred direction? The problem is serious. If this alignment is real, and not measurement error or bad luck, it means cosmology's most basic assumption of uniformity is broken. It's like discovering your house's foundation is crooked, and the entire building structure needs to be re-examined. From how the universe was born to what shape it is, everything might need to be reconsidered. Of course, scientists first suspected they made a mistake. Maybe the instruments had interference. Maybe our Milky Way was blocking the view. They investigated thoroughly, ruling out every possibility. The result? The axis of evil stubbornly remained. So, what does this actually mean? Nobody knows. This leads to some very bold speculations. Maybe there's completely unknown new physics. Maybe our universe isn't flat, but twisted, like a donut shape. Such a strange geometry could indeed create similar alignments. There's an even more mind-bending idea. This might be a scar left from when we brushed past another universe. Of course, it could also just be a super coincidence, like how we always see faces in clouds. Our brains forcing meaning onto randomness. But this pattern has been confirmed by several different cutting-edge instruments and observations. It's hard to dismiss as mere coincidence. The axis of evil hasn't overturned known laws of physics, but it poses a question that nobody can answer. Why does the universe point in that direction? If the universe truly has a principal axis, then all the balance, symmetry, and perfection we once believed in might just be a beautiful misunderstanding. In cosmology, a field that heavily relies on symmetry, such a tiny tilt might hide an enormous secret. Mystery number 6. The missing satellite galaxies problem. This is quite embarrassing. We use the most powerful supercomputers to simulate how the Milky Way formed and discovered the Milky Way should be surrounded by hundreds of small satellite galaxies. Like planets have moons. This is calculated based on our current mainstream dark matter theory, and should be pretty accurate. But here comes the embarrassing part. We point telescopes at the sky and count Counting and counting, we only find a few dozen. Even the Andromeda Galaxy is the same, seriously lacking in smaller companions. Theory says there should be hundreds. Reality shows only dozens. Where did the rest go? This is the famous missing satellite galaxies problem. Scientists scratched their heads and came up with several possibilities. They actually exist. We just can't see them. Maybe these small galaxies are too dim, or never formed many stars at all. Mainly just clumps of dark matter. So, we can't detect them. This explanation makes some sense. We are indeed continuously finding some ultra-faint ghost galaxies. But the numbers still don't add up. They had a chance, but were disrupted. Maybe in the early universe, violent energy bursts blew away the gas from these embryonic small galaxies. Without gas, you can't make stars, leaving only lonely dark matter clumps. The most troubling possibility: our dark matter theory itself is flawed. Maybe dark matter behaves differently than we think. It simply doesn't form that many small clumps. If that's the case, much of our understanding about cosmic structure would be questionable. After all, many of our theories are built on these computer simulations. If simulations are wrong on small scales, can we trust them on large scales? So you see, this isn't just about finding a few small galaxies. It directly relates to whether our cosmic models are accurate. The gap between theory and reality is slowly being filled, but not completely closed. It's like a quiet alarm, reminding us that the universe might operate differently than what we've written in textbooks. Sometimes what we can't see hides the biggest secrets. Mystery number 7: Premature supermassive black holes. We all know black holes come in small and large sizes, but some are monster level, called supermassive black holes, billions of times heavier than the Sun. The strange thing isn't how big they are, but that they appeared too early. We found some of these monsters existing just 700 million years after the Big Bang. 700 million years on the cosmic scale is essentially infancy. Back then, the universe was still chaotic. Stars and galaxies were just beginning to form. Yet, these monster black holes were already there. This makes no logical sense. According to our understanding, black hole growth should be very slow. First, a massive star explodes, becoming a small black hole. Then this small black hole slowly feeds on gas, dust, other stars, growing bit by bit. This process takes an extremely long time. To grow from a tiny thing to it in just a few 100 million years is like a baby growing into yumming in 1 year. Completely impossible. It violates all known growth rules. So, how did they actually form? Scientists have several theories, born winners at the starting line. Maybe they weren't formed from stars at all, but from massive primordial gas clouds, collapsing directly. This would skip the small to large growth process, being born as big babies. These are called direct collapse black holes, but it's still just theoretical. The early universe was a buffet. Eat all you want. Maybe the early cosmic environment was perfect. Food everywhere, dense gas everywhere, frequent mergers, so black holes enter turbo mode, feeding frantically. This explanation works partially, but still feels forced. It's pushing the limits. our understanding of black holes might be wrong. Maybe the way black holes feed, or physics in those extreme environments, works differently than we think. There might be unknown mechanisms that press the fast-forward button on their growth. This discovery is unsettling, because it doesn't just challenge one theory, but shakes our entire understanding of galaxy formation and cosmic evolution. And this isn't just one or two cases. We've already found dozens of these early monsters. Their light has traveled over 13 billion years to tell us of their existence. So the core of this mystery is, how did these black holes grow so large, so fast, in such a short time, in a universe that shouldn't have allowed their existence? It's like finding a grown man among a group of newborns. You have no idea how he got so big until we figure it out. These early supermassive black holes remain a huge question mark on the cosmic timeline. Mystery number 8. Cosmic expansion breaking our models. The universe is expanding. We all know this. Galaxies farther from us move away faster. This speed is called the Hubble constant. For a long time, measuring this speed has been a basic skill for cosmologists. But recently there's trouble. Our measurement techniques are getting better, and we've discovered a fatal problem. We use two of the most reliable methods to measure the universe's expansion rate and get two different answers. Not just slightly different, but significantly different. No matter how we calculate, they don't match. This contradiction is called the Hubble tension. Here's how it works. Method 1. Looking backward, we analyze the afterglow left over from just after the Big Bang, the cosmic microwave background. Based on conditions back then, we can use our best cosmic model to calculate how fast the universe should be expanding today. The result is about 67. Method 2. Looking at the present, we directly observe nearby supernovae and certain special variable stars. They're like standard candles in the universe. By observing their brightness and distance, we can calculate the current expansion rate. The result is about 73. One says 67. The other says 73. This is awkward. The problem is both methods are flawless, both thoroughly tested, and the data is top-notch. Scientists checked and rechecked, calculated repeatedly, but this gap just won't disappear. And the more precise the measurements, the more obvious this contradiction becomes. It's like using two of the most accurate rulers to measure a table. One says 1 meter, the other says 1.1 meters. Who do you believe? So now everyone's starting to suspect. Maybe both rulers are correct, but our understanding of the table is wrong. Maybe it's not a measurement problem, but our entire cosmic model that's flawed. Perhaps the dark energy driving cosmic expansion isn't constant. It might be changing. In the early universe, there existed mysterious particles or forces we don't know about that later disappeared. Or be our understanding of gravity is simply wrong on large scales. This issue is so tricky because both sides appear correct. One is calculated from the universe's baby photos. The other is measured from the universe's adult photos. The two photos don't match, meaning something we don't know about happened during the journey from baby to adult. This Hubble tension is now one of cosmology's biggest headaches. It's like a crack in our existing physics edifice. Though small, it might hide secrets that could change everything. Until we figure it out, this numerical contradiction will remain, reminding us the universe is far more complex than we imagined. Mystery number 9. Strange galaxy shapes and structures. When thinking of galaxies, you probably picture the Milky Ways, beautiful spiral, or a round elliptical galaxy. That's how textbooks show them. Neat and orderly, very regular. But the universe doesn't seem so obedient. When astronomers look into deep space, they find bizarre galaxies, completely breaking the rules. Some look like rings, some like X's, others twisted like abstract art. Nothing like what gravity should produce. The more we observe, the more weird things we find. Here are some examples. Hoag's object. This guy looks like a perfect ring. A circular ring around a core. Clean and simple. Our usual explanation is, ring galaxies form from two galaxies colliding, like water ripples. But Hoag's object is too perfect, and we can't find the culprit nearby. As if it appeared out of nowhere. Polar ring galaxies. These are even weirder. Imagine a disk spinning horizontally, with a ring spinning vertically around it. What an incredible coincidence of collisions would create such a structure. Yet we've found several of them. And various other special galaxies. Cores that grew crooked. Spiral arms twisted like pretzels. Tails stretched extremely long. We always say, these are scars left from galactic battles. But the problem is, what we're seeing are snapshots of crime scenes from billions of years ago. How exactly they fought, nobody can say for sure. It's like seeing only scattered crumbs and trying to figure out how the cake was made. Too difficult. So some scientists are starting to wonder, maybe what we're missing isn't the story, but the physics. Could it be that under certain special conditions, gravity or dark matter behaves differently than we think? Or is there some other force we don't know about causing trouble? Because these bizarre galaxies are right there. Not just one or two, but a whole bunch. We have theories, but not a single one can explain all these weird phenomena. The galaxies we simulate never quite match what we actually observe. So here's the question. Why does the universe create so many rule-breaking objects? Why are some galaxies so asymmetrical, yet not falling apart? Why are some stellar streams so orderly? These questions we can't answer. It's not that we're not trying, but the universe as an architect sometimes just does whatever it wants, leaving us with incomprehensible blueprints. The answer might be hidden in a version of physics we haven't written yet. Mystery number 10, the Great Attractor. Imagine you think you're free, only to discover there's an invisible rope pulling you along. Our entire Milky Way and thousands of neighboring galaxies are facing exactly this situation. We're not just moving outward with cosmic expansion. Our entire large region is being dragged by a mysterious force at over 600 kilometers per second toward the same direction in the sky. This isn't some minor gravitational pull. This is a collective migration spanning hundreds of millions of light years. This mysterious thing pulling us, we call the Great Attractor. This was discovered decades ago. Initially, everyone thought it must be a calculation error. But as observation techniques improved, we found this is real. We really are being dragged by something. The question is, what is that something? We can't see it. It's hidden behind our galaxies. Dustest region. like hiding behind a frosted glass door. Optical telescopes can't see through it. We can only use infrared and X-rays to peek through. The result of this peeking: there are indeed many galaxy clusters in that direction, quite bustling. But when we add up all the visible mass we can see, it's still not enough. That enormous pulling force can't be explained by just these visible objects. So either there's a massive amount of invisible mass hiding there, or something even bigger exists much farther away. Some people speculate the real mastermind might be the Shapley supercluster farther out. That's the largest clump of galaxies in our cosmic neighborhood, but calculations show the direction and force still don't quite match. This raises an even more spine-chilling question. Could it be something we'll never be able to see, pulling us? The universe has boundaries, and light from beyond those boundaries hasn't had time to reach us yet. So, we can't see it? If there's a supermassive structure beyond those boundaries, it could completely influence us through gravity. It's like being separated by a wall. You can't see your neighbor, but you can hear them moving furniture. We still haven't found the definitive answer. This great attractor in science fiction, it's real, tangible motion. We know we're being pulled towards somewhere, but we just don't know why. So, our entire galaxy group just drifts along, not aimlessly, but toward a massive, invisible, mysterious target. It's out there. For decades, we still haven't found it. But it never lets go. Mystery number 11, the Boötes void. Most of the universe is made of space. This isn't surprising. Galaxies might look crowded in photos, but that's only because telescopes magnify the densest regions. In reality, galaxies are like islands floating in an ocean of near-nothingness. But what's abnormal is there's one place that's a bit too empty. It's called the Boötes void. This thing is ridiculously huge, 330 million light-years in diameter. What does this mean? If you took a light-speed ship from one end to the other, you'd fly for 330 million years. During this time you'd see basically nothing. Just pitch black. When astronomers first discovered it, they were stunned. They thought galaxies in the universe were distributed fairly evenly, but when they scanned this region, they found nothing. Logically, such a huge area should have thousands of galaxies. Instead, they found only dozens. As if someone took an eraser and wiped out a huge chunk of the cosmic map. Of course, voids in the universe aren't unusual. Matter distribution is naturally web-like, with dense areas and sparse areas. But the problem with the Boötes void is that it's too big and too empty. So big that our theoretical models can't explain it. So, what exactly happened here? There are several theories. Multiple small voids merged together, like a bunch of small soap bubbles, eventually becoming one giant bubble. Theoretically possible, but the question is, why did only these bubbles merge? Why aren't there equally large ones elsewhere? Born this empty. Maybe at the universe's birth, this region had slightly less matter than elsewhere, so it never developed properly. But this contradicts our belief that the early universe was very uniform, stretched by dark energy. Maybe mysterious dark energy made this region expand faster than others, so matter was diluted more severely. But this is just speculation. since we don't understand dark energy itself. So, the Boötes void remains an unsolved case. It's just there. We can see its emptiness. But we don't know why it's so empty. Some scientists joke that if you were an alien civilization, wanting to hide something massive that you don't want discovered, the Boötes void would be the perfect location, because there's nothing there. Even light would struggle to get out. In all seriousness, this void's existence is actually challenging our cosmic models. If we can figure out why it exists, our understanding of the universe would take a major leap forward. If we can't figure it out, it means our theories definitely have major problems. So you see, sometimes cosmic mysteries aren't necessarily about something, but might be about nothing at all. In cases like this, what we can't see might be the most important. Mystery number 12, cosmic dust that shouldn't exist. Cosmic dust sounds unremarkable, but it's actually the mother of the universe. Without it, new stars and planets couldn't form. Most cosmic structures we see today owe their existence to it. But now there's something strange. We found too much dust, and it appeared too early. Let's first explain how dust forms. It's essentially the slag left after stars burn out. Heavy elements like carbon and oxygen. When massive stars reach their final moments, a supernova explosion ejects this slag, which slowly clumps together into dust. The key is this process takes a very long time. You have to wait for stars to live their entire lives, explosively eject materials, then have those materials slowly cool and combine. Usually it takes several generations of stars. But here's the problem. When the universe was just born, where would heavy elements come from? It was all hydrogen and helium. The first generation of stars had to forge metals from scratch. So logically, dust should be something that appeared much later. But when we used Hubble telescope to look into the deepest universe, we were stunned. In some baby galaxies that formed just a few 100 million years after the Big Bang, they were already packed with dust like giant smokestacks. The timing just doesn't add up. It's like you just started a game. Only 5 minutes in, and you find your opponent is already max level with God tier gear. This isn't scientific. So, where did all this dust come from? Scientists have several theories. The first generation of stars were speed courses. Maybe they came fast and left fast too. Lightning production, lightning explosion, frantically scattering heavy elements. But this speed still can't keep up. Models show it's still not enough. Early black holes as catalysts. Maybe it's the fierce winds from black holes and accretion disks that accelerated dust formation. But this requires extremely strong activity. And not every dusty region has a black hole. Alternative production lines. Maybe there's a type of supermassive star we've never seen that can explode and release massive amounts of heavy elements. But this is just speculation, with no evidence yet. And even if you could make it, you'd still need to preserve it. The early universe was so harsh. Intense radiation, countless shock waves. Newly formed dust could easily be destroyed. So this becomes a deadlock. We can clearly see all that dust. The data is right there. But we just can't figure out how in such a short time it was created and how it survived. This might be telling us the early universe was far wilder than we imagined. The life cycles of first-generation stars might be shockingly fast. Or maybe our understanding of how dust forms is fundamentally wrong. Either way, this dust that shouldn't exist is like a bug in the cosmic timeline? It's there reminding us that our story about the universe's earliest days might be wrong. Mystery number 13. Quasar alignments spanning billions of light years. We always say, the universe on the largest scales is random and uniform, with no direction being special. But this might not be true. There's a type of object called quasars. You can think of them as super bright galaxies, with a massive black hole at the center frantically ejecting energy. This ejection is directional along the black hole's rotation axis. Here's where it gets strange. Astronomers discovered, in a huge region of the sky, hundreds of quasars' ejection directions are surprisingly consistent. These quasars are separated by billions of light years, far larger than any cosmic structure we know. There should be no possible connection between them. Yet their rotation axes all point neatly in the same direction. It's like discovering that all weather vanes worldwide, with no wind present, all point north. This is downright eerie. Scientists ruled out all possible errors, like measurement problems, signal interference, etc., but this bizarre alignment just won't go away. So, what makes them march in unison? Unknown currents or massive structures in the universe. Maybe there's an invisible fiber spanning the cosmos that we can't see. When these quasars formed, it aligned their rotation directions. Birthmarks from the Big Bang. Maybe in the very first instant of creation, space was imprinted with certain directionality, only revealed today through these quasars. The universe's shape is problematic. Maybe the fabric of our universe isn't smooth, but has some twist or structure we haven't discovered. Whatever the answer, this discovery directly challenges the basic assumption that the universe is uniform. If the universe truly has direction, our entire understanding of it, from birth to now, might need rewriting. Mystery number 14. Where did all the antimatter go? This is an even more critical question, directly related to why we exist. According to our most fundamental physics laws, when the Big Bang occurred, it should have produced equal amounts of matter and antimatter. You can think of antimatter as matter's mirror image, like electrons paired with positrons, protons paired with any protons. Physics laws treat them equally, very fairly. But here's the problem: when matter and antimatter meet, they annihilate each other instantly, becoming pure energy. So, if the universe was truly fair initially, creating equal amounts of both, they should have completely canceled each other out. The result would be, today's universe should be empty. Except for radiation, nothing else. No stars, no Earth, and certainly no you or me. Yet here we are. Everything around us is made of matter. So the question becomes, where did the other half, the antimatter, go? Somehow, in that initial great showdown, matter won by an extremely small margin. Maybe for every billion pairs, one extra matter particle remained. It's this leftover infinitesimal bit of matter that eventually formed everything we see today. Why did this happen? Why did matter win? This is one of modern physics' biggest pitfalls, called the matter-antimatter asymmetry problem. We still have no answer. So, why did matter ultimately survive? We don't have definitive answers, but we have several main theories, each more mind-bending than the last. The laws of physics themselves are biased. There's a phenomenon called CP violation. Simply put, physics rules under certain extreme conditions aren't completely fair to matter and antimatter. They slightly favor matter. We've observed this in experiments. We've indeed observed this unfairness. But the problem is, the bias we've found is way too small. Nowhere near enough to explain why so much matter survived in the end. This tiny advantage is completely insufficient. The Big Bang cheated somehow. Some speculate that in the universe's very beginning, during that explosion faster than countless blinks, some asymmetry might have been directly coded into the universe's DNA. Or, B, there existed mysterious particles, or forces we know nothing about, that gave matter a backdoor advantage from the start, letting it win at the starting line. We just live in the matter zone. Here's an even bolder idea. Maybe there are vast antimatter worlds in the universe, and we just happen to live in a safe zone made of matter. But if that were true, at the boundaries between matter and antimatter zones, collisions between matter and antimatter should create spectacular fireworks, producing massive amounts of gamma rays. But we see nothing. The entire observable universe appears to be matter's domain. So, physicists are still desperately searching for answers in the world's largest particle accelerators. They try to recreate the extreme conditions of cosmic birth, hoping to find new evidence of unfairness. Astronomers also scan the skies everywhere, trying to find clues in the universe's oldest light. But to this day, the answer remains a mystery. This issue is so important because it's not just a scientific problem. It directly relates to existence itself. If that initial showdown had been absolutely fair, the universe would have self-destructed long ago, leaving nothing behind. So something must have, at the most crucial moment, quietly tipped the scales toward matter. That one tip created everything we see today. We don't know what it was, but we should thank it, because without it, there would be no stars, no life, only an empty universe. Mystery number 15. Empty space isn't actually empty. We always think vacuum means nothing at all. Absolutely empty. But in physics, especially quantum physics, there's no such thing as truly empty. Space you think is empty is actually quite bustling. It's constantly staging. Something from nothing shows. Countless tiny virtual particles constantly pop out of vacuum and instantly disappear, like a boiling ocean of energy. This isn't speculation, there's evidence. Like the famous Casimir effect. When you place two metal plates very close together in a vacuum, they experience an attractive force. This force isn't gravity or magnetism, but generated by the vacuum itself. This effect has already been measured in laboratories. So vacuum isn't empty. It's full of energy. But here comes the deadliest mystery. Physicists tried to calculate how much energy vacuum should actually contain. When they calculated, the numbers literally exploded. The theoretical energy is higher than what we actually observe, by 10 to the 120th power. You heard right. A 1 followed by 120 zeros. This isn't an error. This is physics history's biggest face slap moment. This problem is so famous, it has a special name, the vacuum catastrophe. Simply put, theory says vacuum should be energy-packed, but reality tells us it's almost empty. What's going on here? Either our quantum theory has major problems at the most fundamental level, or something completely unknown, and even more bizarre, is perfectly canceling out all this massive energy. This problem directly connects to dark energy, that mysterious force accelerating cosmic expansion. Many people suspect it's actually vacuum energy. But if so, why is it so small, instead of as large as theory predicts? This leads to even deeper questions. If vacuum is constantly boiling, could it boil up a new universe? If nothing was never truly nothing, what exactly is emptiness? This vacuum problem is one of modern physics' most fundamental crises, and its biggest crack. We know that what we call emptiness is actually the most active, most important, and most mysterious thing in the universe. The more we study it, the less we understand what nothingness means. Mystery number 16, the lithium problem. In the few minutes after the Big Bang, the universe was like a pressure cooker, fusing the initial hydrogen and helium into some heavier elements. This process is called Big Bang nucleosynthesis. Using our existing physics theories, we can very precisely calculate how much this pressure cooker should produce. About 75% hydrogen, 25% helium, and tiny amounts of other light elements, like lithium. When we actually measure in the sky, we find hydrogen and helium amounts almost exactly match our calculations. Perfect. This shows our understanding of the early universe is correct in the big picture. But the problem lies with lithium. Theoretically, we should find a certain amount of lithium. Not much, but definitely some. But when astronomers searched the oldest stars repeatedly, they found the actual lithium content is only 1/3 of theoretical predictions. 2/3 missing in such precise calculations. This is a huge problem. This is called the cosmological lithium problem. This isn't measurement error. For decades, countless scientists have repeatedly verified using various methods, all with the same result. Lithium is just less than it should be. So, where did this lithium go? Maybe stars burned it up themselves. Lithium is a delicate element, easily consumed inside stars. But models show, even accounting for some burning, it can't explain such a large deficit. Maybe our nuclear reaction calculations are slightly wrong, but this seems unlikely because these formulas accurately predict other elements. If you modify them for lithium, then hydrogen and helium data won't match. It's robbing Peter to pay Paul. Maybe unknown new physics is interfering. Perhaps mysterious particles existed in the early universe that interfered during element synthesis, messing up lithium production specifically. This idea is cool, but pure speculation, with no evidence. So, you see, lithium, one of the universe's simplest elements, has become a small but extremely glaring mystery. It hasn't toppled our physics edifice, but it's like a crack in the wall. You look at it and feel uneasy, sensing something's behind it. In science, often it's these small discrepancies that hide the biggest breakthroughs. Before we find the answer, this mystery surrounding Lee's disappearance must continue to be investigated. Question 17, the fine structure constant. In physics, there's a magic number. It's approximately equal to 1/137th. That number is called the fine structure constant. So, how important is it? In simple terms, it determines the strength of electromagnetism from the stability of atoms. to whether stars can shine. This number controls it all. The great physicist Richard Feynman once said, "This is one of the most damnable mysteries in physics. Because this number, it's as if God casually twisted a knob when creating the universe. If he had turned it just a bit more, atomic nuclei couldn't hold on and the entire world of electrons would fall apart. If he turned it a bit less, chemical reactions would change completely, and life could never exist. But instead, it's just right, not too much, not too little. The problem is, why is it exactly 1/137th? We have no idea. Unlike pi, which can be calculated, this number is purely measured from experiments. Every theory in physics relies on it. Yet no theory, none can explain why it has this value. It just exists out of nowhere. What's more chilling, astronomers discovered this constant might not even be constant. They looked at light from billions of years ago and found the fine structure constant back then seems just a tiny bit different than it is today. If this discovery is confirmed, it could turn the world of physics upside down. A constant that changes over time might mean there's a whole new branch of physics we don't know yet. New dimensions, or perhaps even mysterious forces. This leads to the ultimate question. Why is our universe so perfectly fine-tuned? So precise. Gravity, electromagnetism, and all the fundamental constants, they all seem to be exquisitely designed. Just a tiny change, and none of what we know could exist. Some call it coincidence. Others call it the anthropic principle. Only in a universe like this could we exist and ask this question? So, of course it looks this way to us. And still, some believe there are deeper laws we haven't uncovered yet. And this number, 1/137th, sits right at the center of all these mysteries. It's not just a number. It's a signpost. A constant reminder that we actually know nothing about why the universe is the way it is. We use it every day, from smartphones to nuclear power plants, yet we still have no idea where it comes from. And that alone is a deep and profound